I can't imagine the sadness and anguish you're going through right now, knowing that this is our last help video on 6C, number 9, valence shell electron pair repulsion theory, and the trigonal or trigonal bipyramidal family, and the octahedral family. We reached our final molecule, BrCl4 minus. Well, I can see right here this is charged. This is an anion. So we could actually come straight over here without even doing any of these things and circle that this strongest intermolecular attraction this have is ionic. It is fully charged. That is stronger than dipole attractions and London dispersion force attractions, nonpolar molecules. But nonetheless, we're going to want to find the shape of this molecule. We have one bromine. It is a halogen, family 7. That's 7 electrons. We've got four chlorines in family 7. 4 times 7, 28. We add those two numbers together, we get an odd number. Anytime you get an odd number, you should be hoping for a charge, because doing odd numbered molecules presents a whole different situation. So we have 35. It is charged minus, which means there is an extra electron on there than we would expect. We have to add an electron to it to account for the extra minus. 35 and 1 is 36. We have 36 electrons to work with. Bromine will be in the middle. The 4 chlorines will be surrounding it. And remember, we need to use brackets. So we put bromine in the middle. We would surround it with 8. We would attach a chlorine in each of those spots. And we would replace the shared pairs with lines, surround the chlorines with 8, brackets, and a minus sign because this is charged. How many electrons was it that we had to work with? Well, we had 1, 2, 3, 4, 5 halogens with 7 each. That's 35, and the minus charge took it to 36. So we look at how many electrons we have here. We have 1, 2, 3, 4 chlorines, each surrounded by 8. That's 32. So what do we do to fix this? We have to add pairs of electrons. We have to add 2 pairs or 4 electrons on the bromine to get our total to the 36. And that should be good for our molecule. Let's analyze its shape. Even though we know the strongest intermolecular force is ion to ion attraction, we'll still want to take a look at the shape of this molecule. To look at the shape, we need to see how many things are on our central atom, bromine. We have 4 atoms, that's 4, and we have 2 sets of lone pairs, that's 5, that's 6. We have 6 total things on that central atom. Those 6 things immediately put it in the octahedral family. As we saw in other videos, there are 3 members of the octahedral family. We've got octahedral, which is a 6-0, square pyramidal, which is a 5-1, and square planar, which is a 4-2. We saw we had 4 atoms bonded to the central atom. There's the 4 chlorines. And we had 2 lone pairs on the central atom. Here's our lone pairs. That is a 4-2, and the 4-2 is square planar. With the 4-2, we can complete our shape formula or Vesper notation, AB4E2, that's 4 bonded atoms, 2 lone pairs. Here's the square planar shape. We lost the pair that was on, or we lost the atom that was on top. So when we go through the octahedral family, the first member of the octahedral family has an atom up and an atom down and 4 in the equatorial plane. The first atom we lost as we progressed through the family was atom number 6. When we lost atom number 6, an axial atom, we were left with the square pyramidal. Then going from the square pyramidal to the square planar, we lost this atom right here. And we're left with a lone pair of electrons, leaving us this shape right here. So we no longer have any atoms in the axial plane. So our axial to axial angle, there isn't one. Since there's no axial atoms, we don't have an axial to equatorial angle. We just have the equatorial angles of 90. So now we come in here. Now that we know we have 2 lone pairs, we can proceed out to try to figure out the symmetry of this atom. As we proceed out, E does not equal 0, so it's not symmetrical. So we head up this path where E does not equal 0. In order for it to be symmetrical, E had to equal 0. So heading up this way, E equals 2. So we check down this line. Is the molecule a 4-2? It is. So this is categorized as a special type of symmetry. When we say special type of symmetry, the reason it's special is because the atoms are symmetrical. Those atoms are symmetrical, but we have two different things on the central atom. We have atoms and we have lone pairs. So overall, the molecule is asymmetrical, but the atoms themselves are symmetrical, which means that if there were polar bonds, they would cancel each other out. So if this atom's poling, it's canceled out by that atom. If this atom's poling, it's canceled out by that one poling, if there were polar bonds. So that would take us to the fact that this molecule would be nonpolar. However, as we learned early on, this molecule had a charge. This molecule is ionic. So whether it's polar or not doesn't really matter because our strongest attraction is ionic. In terms of having the same or different atoms on here, again, it wouldn't matter that much. They are the same atoms. Why wouldn't it matter if they were different? Because our stronger force is ionic. They have the same atoms. That should wrap up this molecule. And that should wrap up our discussion of 6C9. If you have questions that were not answered in the video, please don't hesitate to contact me. We can discuss any questions on 6C9 that weren't discussed or answered in the video. Thanks for watching.